All right, so let's imagine that we have the following alkene. And we're going to subject this alkene to ozonolysis. So the reagent in the first part of the reaction is simply ozone. The second part will have a reducing agent like dimethyl sulfide. And the whole idea with ozonolysis, before we get into mechanistic details, a little trick I learned in graduate school with ozonolysis. There are 3 oxygens in ozone. One, two, three. Now ozone has the following structure, and of course it's resonance stabilized. But just in terms of how the bonds are made, I'm going to break a carbon-carbon double bond, and those are going to be replaced with carbon-oxygen double bonds. So 2 of the oxygens, one will go here, one will go here. And the third oxygen is going to oxidize my reducing agent. Remember, reducing agents are themselves oxidized. And so I'm going to get DMSO as a side product. So this is what you're always going to get. Now, if I had these 2 reactants and I were to react them with titanium chloride, this is called the McMurray coupling, I would do the reverse reaction. So the McMurray coupling is the reverse of ozonolysis. So let's take a look at some mechanistic details now. Of course, the oxygen that is making 3 bonds is going to be positively charged. The one making 2 is neutral, and the one making 1 is negatively charged. So it is an ylide because you have 2 nuclei that are making a covalent bond one to another. One's positive charge, one's negative charge.
Okay. Yeah, I can do that.
So you're going to have nucleophilic attack. You're going to break a pi bond to make a lone pair. And then on the developing positive charge on the other carbon that was formerly engaged in the pi bond, you're going to have nucleophilic attack from the O-. This produces an intermediate called a malozonide. Here's our malozonide in this particular example. And of course we have lone pairs. In terms of mechanistic pattern, this is obviously a nucleophilic attack. As with all electrophilic addition, the nucleophile are the pi electrons. Now let's look at the second step of the reaction. In the second step of the reaction, you're actually going to, first we cleave the pi bond, now we're going to cleave the sigma bond. So this is the bond that we are going to break. So as we break this bond, these electrons will form a pi bond. This oxygen-oxygen bond is going to break and will result in a third set of lone pairs around the following oxygen. And one of these lone pairs will make a pi bond between this carbon and this oxygen. So I would label this as loss of a leaving group. You'll talk a lot more about loss of a leaving group when you get to SN1 and SN2 mechanisms. So what we have acetaldehyde as one product. And then we have this guy. In this next step, we're going to have nucleophilic attack, this time onto the carbonyl carbon. So the nucleophilic attack is from the negatively charged oxygen. This bond is going to break and leave a lone pair, and one of these lone pairs is going to attack this carbon, and of course this pi bond breaks and makes a lone pair on oxygen. This results in a net rearrangement from a malozonide to an ozonide. So let's track this very carefully. What I want to do is number the carbons. I have carbon, I'm going to call this carbon 1. I'm going to call this 1 prime because it's attached to carbon 1. I'm going to call this carbon 2. I'm going to call this 2 prime because it's attached to carbon 2. I'm going to call this 1 double prime, 1 triple prime, and 1 quadruple prime. Just so that I can understand that I'm going to make a bond between carbon 1 and carbon 2. Well, actually, that's not quite correct. Let me go back here. The bond that I'm making is going to be between carbon 1. Remember, carbon 1 has a methyl group and it has a propyl group. And I'm making a bond between an oxygen. In fact, it's the oxygen that was attached to carbon 2, so I'm going to call this oxygen 2. Carbon 1 is also bonded to an oxygen. Which is bonded to an oxygen, which is bonded to carbon 2. In fact, let's do this with a terse structure. Of course, this is nucleophilic attack again. But more important than that is if I look at the loss of leaving group step and the nucleophilic attack step, going from the malozonide to the ozonide, it's a net rearrangement. This is unique because it's not a carbocation. It's usually carbocations that rearrange. And of course, on carbon 2, there's also a methyl group. And again, this is called the ozonide. Now, let's look at how we are going to end up with our carbonyl products. course, sulfur is going to have 2 lone pairs. So we're going to end up having something like the driving force for this is cleavage of an oxygen-oxygen single bond. So this is going to go here. This is going to go here. And this is also going to go to the sulfur. What this means is that I have a ketone, plus I have a 2-carbon aldehyde, acetaldehyde, plus I have DMSO, dimethyl sulfoxide. Notice the source of the oxygens are from the 3 oxygens of ozone. So since this molecule is oxidized, I'm actually reducing this entire complex. That is ozonolysis. Okay, so now let's look at electrophilic addition of excess HBr to an alkyne. So the first step in this mechanism, predictably, is going to be a proton transfer. And Markovnikov's rule is in play, which means I want to generate a carbocation that is more resonance stabilized. Well, actually, not more resonance stabilized, because that's not relevant here, but what is relevant is hyperconjugation, a more substituted carbon. So what that means is I'll form the carbocation right here, and I will have attached, I'm going to circle the hydrogen we just added via a proton transfer, whereas this other hydrogen was already there. Because this carbon is bonded to 2 other carbons that have electrons that can begin to help stabilize a weak pi-pi overlap. And so this is a proton transfer, and then Br minus is the nucleophile that's going to react with this highly reactive carbocation intermediate. And so once this is accomplished, I have a vinyl alkyl bromide. So I still have the double bond, but now I'm bonded to a bromine. Since I have an excess of HBr, I simply repeat the proton transfer and the nucleophilic attack again. Now, resonance is relevant. It's not a huge contributing factor, but the carbocation that is on the carbon attached to bromine is more stable. So again, here's the new carbon-hydrogen bond that I made. Here's the one I made from the previous step. This is the one that was already attached to the molecule. The reason that resonance is relevant here to a small extent, bromine doesn't easily make 2 bonds, but I can have a resonance stabilized intermediate. This is really going to pull electron density away from this carbon. And now Br minus, which is also in solution after the proton transfer, is going to attack this carbon, and this pi bond breaks to regenerate the lone pair. So 2 equivalents of HBr will result in both of the hydrogens and both of the bromines being attached to the same carbon. This is called a geminal dialkyl bromide. Geminal means that both bromines are attached to the same carbon. When I reacted this with an alkene and I would add Br2, I would get a vicinal dibromo, which means they're attached to adjacent carbons. So this is the major product when I use an excess of HBr.
The anti-addition?
It's not anti. Let's look at a couple of advanced alkyne reactions as well.
Don't you do that with water?
So the first set of conditions, we're going to use HgSO4 and H2SO4. So your relevant electrophile is Hg2+. And again, it has a reactive lone pair. So the pi electrons, you got four pi electrons now, so that it's even more nucleophilic than an alkene. And of course, this will attack the carbon on which the positive charge is developing. And you're going to get a mercurium ion intermediate like with alkene addition, only now you still have a pi bond. And so you have a double bond. I'm going to show one stereochemical result. The secondary like carbon is going to be more electrophilic because it can better stabilize a positive charge. And so now water, of course if we have sulfuric acid, it's an aqueous solution. Water now opens that's an SN2 attack where, of course it's not relevant here because, and I'm just going to go ahead and show this being deprotonated because this isn't a chiral center since carbon's engaged in sp2 hybridization. And this will be replaced by a hydrogen. I have a vinyl alcohol. This vinyl alcohol will tautomerize. What this means is that I can have it base catalyzed or acid catalyzed. For example, let's look at it being acid catalyzed because we have sulfuric acid. This gets rid of the double bond. I'll have a carbocation right here, but that's fine because very quickly oxygen adds one of its lone pairs. And now the conjugate base of my acid. Now, in all honesty, it's not going to be sulfuric acid. It's going to donate that to a water molecule, so the acid is going to be hydronium. So another water molecule comes in, acts as a base, and the driving force is to regenerate the acid catalyst and to neutralize my carbonyl because this has a positive charge, but not after this proton transfer occurs. And so my final product, when I react a terminal alkyne with HgSO4 and H2SO4, is I get a ketone. Now, I've talked about borohydration on a couple of other videos, so I don't want to get into mechanistic details here. But borohydration is anti-Markovnikov. So what is going to end up happening with a molecule like this is that the OH attaches to carbon 1. And after it tautomerizes in a similar fashion to what we just saw with the ketone generation, you're going to get an aldehyde. So if I have a terminal alkyne and I hydrate with mercury catalyzed conditions, I'll get a ketone. With borohydration, however, I will get an aldehyde. The conditions for borohydration, some kind of borane, so you might see BH3, B2H6, 9-BBN, which is just a more sterically hindered borane. You'll have tetrahydrofuran or THF as your solvent. And then in the second step, you'll have NaOH and hydrogen peroxide. Again, I've done the complete mechanism on previous YouTube channel videos, so just go and look those up.